Hey everyone, welcome to Game Tools. This is going to be a series that's going to focus mainly on some smaller bits like graphics, a little bit of mathematics, just everyday tools that you use for game development in general, but it goes to a lot of specialties and a lot of various areas that you could use in your career. Today, let's look at this given example. So here we have a game board, we have Pac-Man, and then we have two dots. And here's the question. In this frame, we want to move Pac-Man towards the closest dot at a constant speed of 0.5 units per frame. Now you might be asking yourself, how do I solve this? Some of you might already know, but the tool that we're going to use today is vectors. I'm going to go over what those are and then kind of give you an example of how we could solve this given problem using those tools. So a vector itself is split up into two necessary components. The first component is the magnitude. That's the scalar bit. Scalars can be represented as any kind of single number, such as speed. For this instance, we have 5 miles per hour. A distance could be a scalar, or volume. Now, a big misconception is that something like speed is the same thing as something like velocity. However, speed only tells you how fast you're moving along a given direction. It doesn't tell you what the direction is that you need to travel in. So, along with the magnitude, you also need the direction component for a vector. The magnitude, again, just tells you the length along the direction that you're traveling. The direction itself tells you which direction you're going to be traveling in. To illustrate this a little bit, here we have a unit circle. It's a unit circle because it has a radius of 1 unit. And then in the center of that, we can imagine drawing lines that go from the center of the circle to the edge of the circle and touching its tangent. Each of these are considered to be unit vectors because each of them has a vector of a magnitude of 1 unit, and they all encode a direction into them. Now, extending that, we can combine the magnitude and the direction in order to get from this unit circle any number of vector that extends beyond the unit vectors. I think one thing that needs to be made clear is that vectors aren't necessarily positions. For a position, it's considered a point vector, and it starts at the origin in a given coordinate space. So if we're in a 2D coordinate space, this would be our position vector here, a position at 3, 4. And all it is a vector that starts from 0, 0 and extends outward towards 3, 4. And that could encode a position. However, if we look at this example over here, we have the exact same vector, which again is just a direction and a magnitude. It just has different origins and different starting spaces for these two different vectors. So again, they're the exact same. If we were to stack these on top of each other, you would see that they're the exact same vector. They're just starting in different locations. All right, so let's look at some common operations that we could use with vectors. First, we'll talk about addition, which we'll denote with a plus b, vector a plus vector b. If we have a vector a, which has an x component and a y component in 2D space, and then we have a vector b, which also has an x component and a y component, then a plus b is simply a vector that has components ax plus bx, and then ay plus by. For a concrete example, we can look at this. Say that we have a vector a, it's a vector with x component 1 and y component 2. Then we have b with x component 3, y component 4. Then a plus b is going to be 1, 2 plus 3, 4, and that gives us 3, 6 for our final vector. We can do the exact same thing with subtraction. It's just going to be subtracting instead of adding the individual elements. So again, the exact same setup, but instead of adding these two vectors, we're going to subtract them. So it's 1, 2 minus 3, 4, and that gives us a final result of -2, -2 for our final vector. We can also multiply scalar values into a vector. So here we have some scalar s multiplied into a vector a, and we can write this out as the x component of the a vector times the scalar, and then the y component of the a vector times the scalar. And here we have an example. Let's say that we have a scalar 4, and we're multiplying that into a vector that's 1, 4. That gives us a final vector of 4, 16. Finding the magnitude is also very important. This gives us the total length of a given vector. The operation for that is very simple. It's just going to be the square root of our x component squared plus the y component squared. So let's look at an example. If we have a vector 3, 4, then the magnitude, which is denoted with this symbol here, the two lines on either side of the vector, that's going to be the square root of 3 squared plus 4 squared, which gives us square root of 25 or 5. And finally, let's look at normalizing a vector or finding a unit vector. This is also called finding the direction of a vector, which again, remember that vectors are magnitude and direction. So for this, we'll denote the vector with what's called a hat. So we'll call this a hat. And what that is, the operation is the original vector a divided by the magnitude of that vector. And if we take this out further and actually show what this looks like, it'll be the vector a divided by its magnitude, which this operation, again, is just a scalar. So we're going to divide the x component by the magnitude, the y component by the magnitude, and then that'll give us our final normalized vector. Here's an example. Let's say that we have a vector 3, 4. Finding the magnitude first is going to be, again, the square root of the x component squared plus the y component squared. So in this case, 3 squared plus 4 squared, which gives us a value of 5. And then finally, normalizing our original vector, we can do 3 divided by 5 and 4 divided by 5 for our final normalized vector. You can guarantee that this is a normalized vector by checking the magnitude of this vector. If it comes out to a length of 1 or a value of 1, you know that it's a normalized vector. All right, so going back to our original question, let's go back to the game board where we have a couple of goals that we want to define and we want to find. We write them here. We want to find the minimum distance between these two dots and Pac-Man itself in order to be able to select the closest dot. And then we want to update our position for this frame so that we move Pac-Man in the desired position. So the way that we can actually define the vectors that we're interested in is going to be subtracting position from another position, which will give us a vector in space. So for our first vector, A, this is going to be the first dot's position minus Pac-Man's position, which gives us position 5, 5 minus position 2, 1, and that'll give us a vector of 3, 4. Now, again, we're interested in the distance from Pac-Man to this dot. And the distance, again, is going to be the magnitude of this vector. So we want to find the magnitude of the new vector that we just found. Again, that's denoted as this. The magnitude of A is going to be the square root of the x component squared, so 3 squared, plus the square root, or the squared y component, 4 squared, which gives us square root of 25, or 5. Now, let's look at B. So we have B, I'll write it over here, is going to be 0.2 minus 0.0, which is 6, 1 minus 2, 1, which gives us a vector of 4, 0. And then if we look at to find, again, the distance that this vector represents, the magnitude of this vector will be the magnitude of B. It's going to be the square root of the x component squared, so 4 squared, plus the y component squared equals the square root of 16, or 4. So if we look back to our original question, we wanted to know, find the minimum distance between the two, and that's going to be our selection metric. So if we go back to here, we have first dot, let's call it dot 1, is a distance of 5, dot 2 is a distance of 4. The minimum of these two is going to be this one here. So we're interested in this dot. That's the one that we've chosen. So we've solved our first part. Now we have an issue. We've solved the first part, but that doesn't tell us necessarily how we need to move. If we look back at the vector that we've chosen, that's going to be B. It's 4, 0. Now what we want to do is we want to find some velocity vector, some movement vector that moves Pac-Man in this frame towards that given goal. However, if we apply this 4, 0 to his position, what that means is that we're going to be moving at a speed of 4 units per frame, which is too fast. We want a speed of 5 units per frame, or 0.5 units per frame. So what we need to do first is we need to take this vector and we need to find the direction for that vector. Let's do that now. So again, the direction for the vector is going to be a normalized vector. And again, just to remind you, that's going to be the original vector divided by the magnitude of that vector, which in this case, it's going to be 4, 0, divided by the magnitude, which is 4, which gives us 4 divided by 4, which is 1, 0 divided by 4, which is 0. And this will be our direction. And again, we can check to make sure that this is a unit vector by taking the magnitude of this. If we do that, we get the square root of 1 squared plus 0 squared, which is the square root of 1, which is 1. And that's what we expect with a unit vector. Now we can apply any kind of scalar quantity, scalar value, which in this case is going to be our speed, in order to control the magnitude of this vector. That's what's so powerful about normalized vectors. Let's go ahead and clear some of this up. So now we can find our final velocity, which let's denote that as v, is going to be our speed, and then we're going to multiply that with our direction. So that's going to be a speed of 0.5 units per frame. Multiply that by our direction, which is 1, 0, And that gives us a final velocity vector of 0.50. Now that we have this piece of information, we can now apply it to Pac-Man's current position in order to get our new position for this frame. So our new position, which we'll call PF for position final, is going to be our current position plus the velocity that we're interested for this frame. So that's going to be our current position, which is 2, 1, plus the new vector that we just found, which is 0.50, which gives us a final position of 2.51.